is this session. Okay, so we're starting chapter 4 today. So in chapter 4, this is dealing with graphing and kind of basically just understanding exponential functions. So this is going to be dealing with exponential growth functions and just exponential functions in general. But let's add in this growth word because that's specifically what we're going to do like just in today's section. So when you're talking about a growth function and a function that's growing exponentially, the one thing that I really like to kind of bring into this, and I know the whole year has been talking about COVID, but COVID in general is a perfect example of exponential growth. So when something is growing exponentially, it basically means that you start with something small and you get to something super big in a short amount of time. So when you think about a graph of that kind of a function, we start low and we spike up high really quickly. Okay, some of these might take a little bit longer to spike, but regardless, as soon as you start to grow, that growth happens like very, very, very quickly. So I like to talk about this with the coronavirus because let's say that this girl is me, okay, and I contract coronavirus. So say all of a sudden, I'm going to put a positive on my head because I become positive. But here are 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's say I have 12 people that I have been in contact with, like close contact, so within 6 feet for more than 15 minutes. Say these are the 12 people that I've been in contact with. These 12 people all now have the chance of being sick from just me. So say I went to China and I brought the virus back. I'm the first person to have it in the US. And these 12 people now all have the possibility of being positive. Let's say these 3 people don't have it, but these 9 do. Now each of these 9 people have 12 people that they've also been in contact with. So I went from tier 1 of me to 9 people to these 9 people's other 12 people. Okay, so you kind of see how that just like grows exponentially. Started with me, then by 9 people, then all of a sudden way up here at 1,000, and then 10,000, and then 1,000,000. And then all of a sudden we have a global pandemic because one person infects 15 people, which infect another 15 people apiece. So we went from just one person sick to millions of people sick because of the fact that that virus can grow exponentially. Does that make sense? Okay, I can't really see your head, so let me pull you in here really quick. Are we doing good? Okay. So graphing this is not my most, it's not my most important thing for you. So while I want us to be able to graph them, I'm going to show you one quick example. Because quite frankly, it's not like this is how we graph a quadratic function where you find the vertex, find the x-intercepts and y-intercepts and graph it from there. You truly make an XY table, and that's all you do when we're graphing these. So I don't want to take a ton of time with this because it's much more probably simple than you can make it out to be. So when we think about an exponential function, it's going to be in a form of 2 numbers multiplied together with an x in your exponent. So why do you think they're called exponential functions? It's because your variable is in your exponent. So anytime that we are discussing like the name of a function, a quadratic function is because the variable is being squared. Cubic function, because the variable is being taken to a cube. When we talked about square root functions, it's because the variable of x had the square root of that variable. So you're always talking, like the name of a function comes from what's being done to the variable. Since the variable is in the exponent, it's an exponential function. But this is why they grow so quickly. Okay, when you think about taking a number to an exponent, let's just think about 3, for example. 3 squared is 9, but 3 cubed is already up to 27. So 3 to the 4th grows even quicker and quicker and quicker, and soon we're at this massive number just by taking 3 to some exponent. So whenever you have a number in that exponent, it's going to be increasing really rapidly, especially when that number is a variable, because that variable can be any number. It could be 1, could be 5 million, it could be anything. So I want us to graph, and again, really quick, one example. Let's do an easier one. 2x, sorry, not 2x, 2 to the x. Okay, 2 to the power of x. Sometimes my marker flattens out, you can't really tell. That's an x up there. So we know that exponential functions take some kind of form, again, where they start low and they jump high when they are a growth function. Okay, so we know that we're going to take some kind of curve like this with this function. We just have to figure out what specifically will that curve be. So again, we just start up an XY table. That's all we're going to try with this. So let's start up a graph to think, what kind of numbers do I want to test? Again, I'm testing my X values. Okay, and I think if you guys talk now, you're okay. It's not going to change the screen. So if you want to burst anything out there, feel free. Okay. So let's think about X values. What do we want to test? Looking back at this graph, there's stuff happening to the left side of my y-axis. So I do want to test at least a couple, if not more than that, of my negative X values. So let's start maybe just up at -2 and just think about, well, let's just try -2. You can do this either in your head or in a calculator. It doesn't truly matter to me, whichever way kind of works for you. But 2 to the power of -2, right? When we're testing an X value, we put that X value into our original function. So this will be 2 to the -2. When we have a negative exponent, what does that mean? Do you guys remember what do negative exponents do to us? Any of you guys remember? You can type it. Sorry, go ahead.
They go to the denominator.
They go to the denominator. So we say 1 over 2 to the positive 2, which becomes 1/4. So we had the point -2, 1/4. Let's go graph that. It's going to be super low here down on our graph. Okay, super low down on that graph. Let's just keep working from left to right. So let's go ahead and test -1 now. We might as well at least see what's happening there because we're already on that left side. So 2 to the -1, again, we drop that down to our x, to our denominator, and make that exponent positive. So it's now 1 over 2 to the +1, which is just 1/2. So -1, 1/2. So we go up a tiny bit. We go up from 1/4 to 1/2. Let's test 0. This is one property that hopefully you remember, 2 to the 0 power. Any number to the 0 power equals, anybody? I know it's over Zoom, but you can still talk. Close, Raylene, close. Not 0.
1.
1. Anything to the 0 power equals 1. So 0, 1 is the next point on our graph. Let's do 2 more numbers. Let's do 1 and 2. Putting in 1 for x gives us 2 to the first, which is just 2. 2 squared equals 4. So 1, 2, and 2, 4. So you can see that this is already starting to take that curve. So we can connect these dots and signal we're going to keep going up forever where we're growing incredibly rapidly. Going over to 3, we're already way up here, 4, way up here. It's only going to continue doubling, tripling, quadrupling until we get way up into infinity. Okay, so anytime you're faced with trying to graph an exponential function, we jump straight over here to an XY table. Being smart that you have likely some on the left side of your y-axis and some on the right side of your y-axis. If you kind of hang around these middle 5 numbers, you'll find a pretty decent exponential graph. Okay, any questions on that? Awesome. Okay, so I am a lot more interested in the real world components of how we can deal with exponential functions. So if you've taken a science class with, I'm trying to think who teaches the one where they do this. They deal with half-life of bacteria, and they also deal with half-life of like medicine or elements, and then the growth of bacteria. So think about if you've taken that science class, when you think about the growth of bacteria, it multiplies so incredibly rapidly. It's kind of like the coronavirus, right? You start with one little bacteria, then you come back maybe in a day and you have like 1,000 of those bacteria, and you come back the next day and you have like 1,000,000 of those bacteria. Oh, good question, Ashley. So the way we decided let me put that back up there. The way we decided what numbers to test for x, we know that exponential functions generally hang out here in the middle, okay? Let me exit this out really quick. Those exponential functions hang out around in the middle. So we started with -2, and if -2 had produced a super big number, we would have kept moving back this way. We want to try to get to the root of those fractions. So you should always be able to find like your least or most smallest number and then start working up from there. So once you find a small number on the left side, you start working your way to the right. We need about probably 4 to 6, maybe even 7 points, but 5 is kind of a good number to stop at. Does that help? Let me grab my chat again. Does that help, Ashley? Okay. So when we're dealing with actual real life examples of trying to use exponential functions in our actual real life, what we call those specifically is like our exponential growth models. Okay, and the model for this is we're going to have an A value on our outside. So an A is out here with 1 plus R inside of the parentheses. And then this will be taken to the power of T. Okay, I'll let you get that written down. I'm going to grab this chat really quick and make sure. Okay. So the best way to kind of explain this, I'm going to step out of the way so you can kind of see the board. The best way to explain this is by showing you an example. So when we're talking about A, it depends on the kind of example you're gathering, but it's generally what you start with. And your R is your rate. Likely it's going to be in a percentage. So a percentage that you might be given. And then T is always going to stand for time. So I'm going to, and I'm gonna let you get that written down before I give you our last kind of likely example for the day. Oh, it's only 26. Okay, my clock is ahead in my classroom. So you're getting that written down. Okay. All right. Let me write it up here. Let's see how tall I can be today. So in 1996, there were 2,573 computer viruses. So you gotta just think about, computers were like barely a thing in 1996. So that's not that many viruses, but was for the time that it was in. So during the next 7 years, the number of viruses increased by 92%. Each year. Okay, what I want us to do with this information is I want us to write the exponential growth model for the number of viruses after T years from 1996. So it's going to be a two-part example here. I do need to erase this. I'll bring it back up in a second. So we're first going to write the exponential model. Then what I want us to do is use this exponential model in order to predict how many viruses occurred in 2003. All right, I'll give you another couple minutes to get that all written down. So in 1996, there were 2,573 computer viruses. During the next 7 years, the number of viruses increased by 92% each year. Where I want you to A, write the exponential model, B, use the model to calculate the viruses in 2003. So again, here is, you can see this side. Here's what that model looks like. Y equals A times 1 plus R to the T. I gave you what all of these different kind of variables are used for. So if you're comfortable, go ahead and start trying to write this model. Given what all those different variables mean, that A is what you start with, R is your rate, and T is your time, you can go ahead and try to write a model for it, keeping in mind we don't put a variable in for, or a number in for our variable of our exponent. Okay, so let's write this exponential model. So again, when we're talking about our A value, that is what we're starting with. So how many viruses do we start with? 2,573. Okay, 2,573. Then we need to input our rate. So 1 plus our rate. Our rate is 92%. I want to ask you this question though. Do we ever use percentages when we are discussing, like when we're trying to put something into a calculator? Would you put in, like if you're trying to figure out sales tax, would you say like, oh, I need to multiply my dollar double cheeseburger by 6%? You would have to calculate that percentage into a decimal. So if we have 92%, the decimal's over here currently. You have to move it 2 places to the left. So what was 92% is the decimal 0.92. Super important you calculate that into a decimal each and every single time. So 1 plus 0.92. We can add this really quick. 1 plus 0.92 is simply 1.92. And then we need our exponent. Be really careful when you're asked to write an exponential model. So a model is something that can be used over and over and over. So in the example they gave us, that this is what happened after 7 years. But what if I want to go ahead and find what happened after 15 years? What's happening in 2020 now? Okay, you have to leave that time or that variable the same. So I'm going to input a t so that anyone that comes in later on can use this model to figure out, well, what if we want to know what's going to happen in 2050? How many viruses are we going to have then? They can use this model to figure that out, but they can't if I put in a time for them. So here's your model. Now use this model to calculate how many viruses occurred in 2003. Okay, so what I need you to do is figure out how many years have passed by 2003 from 1996 and try to give me a total number. Okay, we have a couple more minutes. This will be our last example. I just want to wrap this up, but I want to give you about a minute to try this one on your own. And let me pull you guys back over. Quentin, make sure you're trying it. Okay. Whoop, that's not what I wanted. Okay, another like 30 seconds. Okay, so what number should we have input for t here? How many years have passed since 1996 to 2003? How many years does that represent? Not quite 8. You're skipping one. You're skipping one, but you're adding one too many. So think about the years between 1996 and 2003. We're talking about 7 years. Okay, so t should equal 7 here. So we have 2,573 times 1.92 all to the 7th power. So notice the parentheses I put in here. You would have needed these parentheses when you type this into your calculator as well. I don't have a calculator near me. What did any of you guys get for your answer? Anyone want to type it in? Or do the calculation really quick for me because I have no calculators near me and I can't do this in my head.
Miss Norman,
Yeah.
So do you take your exponent and do it to the 1.92 and then multiply the two numbers, or do you add them?
Good, so you wanna type it in just like this, you have this front number, and then in parentheses, your 1.92, then to the exponent of 7.
Okay.
So I actually didn't realize I had this written down. Are you getting, sometimes last year I did my calculations wrong too. 247,484, about that many viruses. Are you guys getting that?
Yeah, that's what
Yeah, there we go, it's in the chat, thank you.
I
Okay.
also got 7 too.
So not incredibly difficult, right? You have to pull the missing pieces, try to forget about some of the stuff in there that's not necessary in the moment. But essentially, you have what you start with, the percentage you're using, and then for how long that's going to go on. Tomorrow, we're going to get into more of what's called compounding interest rates. So we're gonna have you try to figure out how to make the most money from what you have. So that's tomorrow. If you guys have any questions, please bring them tomorrow. You have no homework for tonight though, okay? Sound good? Awesome. Have a great day, guys. Happy Monday.
Adios.
Adios.